Hi and welcome back. Today we're going to look at the last of the organic pathways that we need to know for HL, and this is reduction reactions. So let's get started. We know and have studied before the idea of oxidation reactions, where we add in oxygen into a species and it becomes more oxidized. So we can see here with the different stages of methane that methane going to the alcohol through to the aldehyde, the carboxylic acid, and eventually carbon dioxide is its most oxidized form. So we also know that for every oxidation reaction, there is also a reduction reaction, forming a redox pair. In organic chemistry, rather than following the half equations which we know how to balance with coheres, it can often be easier to think in terms of oxygen-hydrogen loss and gain when looking at complex molecules. For reduction reactions, we think about reduction being defined as the reactant gaining hydrogen, i.e., if we were to think of going back this way, we've added two hydrogens in here, so the reduced form of carbon dioxide is the carboxylic acid. All the way back to the fully reduced form would be methane. So if it's got more hydrogens on it, we consider it to be reduced. That means that we can reverse the oxidation process of alcohols or things like that and reduce them in turn. So we can see that with the primary alcohol, we know how to take it from primary alcohol to aldehyde and carboxylic acid, remitting that we do this, we heat this with acidified potassium permanganate or acidified dichromate. Okay, with heat, this one being to distill off as it forms, and then this one we heat under reflux to make sure that we get all the acid. And we can do the same thing, we can reflux a secondary alcohol in the presence of a strong oxidizing agent and get the ketone. What we're going to do now is look at the fact that we can actually reverse these reactions. We add either of the following reagents. These are strong reducing agents, and that is sodium borohydrate in aqueous alcoholic solution. Notice that it is in an alcohol solution, so sodium borohydrate, or lithium aluminium hydride, lithal, L-I-A-L, so lithium, aluminium, and then 4 hydrogens. In anhydrous conditions, so this means without water being present, which means that we use solvents such as ether. And you may remember ether with the ether functional group being in this, and it can be diethyl ether or ether, but primarily we use dry ether, and then we have to treat it with an aqueous acid, and we'll look at why that's the case. So where we use the symbol with the square brackets and the O to indicate oxidation, because we were adding in oxygen, for reduction we can use the symbols with the square brackets with the hydrogens indicating reduction. So we can go from the aldehyde back to the alcohol, or the ketone back to the alcohol. With the other things that we can do is we can look at the reduction of carbonyl compounds such as carboxylic acids and ketones. Again, we're going to be looking at heating these with lithium aluminium hydride in dry ether, and it can't be stopped at the aldehyde because it reacts too readily with the strong reducing agent. Okay, again, it goes via the aldehyde, but this time it's a transition state that we can't isolate, okay, or an intermediate that we can't isolate, and then we get back to ethanol from our ethanoic acid, ethanol from our carboxylic acid. We have to do these under acidic conditions so that we are reprotonating these acids. And same goes for our ketones and secondary alcohols. Just the same as when we did our oxidation reactions, they also had to be under acidic conditions. For the ketone, we use sodium borohydride to get the secondary alcohol. Just as we talked about making nitrobenzene the other day with our electrophilic substitution of benzene to form nitrobenzene using the nitrating mixture, we can form the amine, otherwise known as phenyl because of our aromatic group phenylamine. So we've added an NH2 onto the benzene ring in a two-step reduction process. First, we need to make the nitrobenzene. Then from there, we react it with tin and concentrated HCl. What this does with heat and reflux is protonates our nitro. It turns it into NH3+. So we reduce it and we form the NH3+ ion, which is our phenylammonium ion. We don't want the ion, we want to make this a amine. So then we react it with sodium hydroxide to remove the hydrogen from this protonated amine. Remember, amines can act as bases, but they're a weak base if we add, so they're not going to hold on to that proton very well. So they're going to be a proton acceptor. This has accepted a proton. If we add a strong base, it will now act as an acid and donate that proton to form the non-protonated neutral phenylamine and water. That's it for our reduction reaction. So all you need to do is be able to remember the reagents, the lithium aluminium hydride, which we use for our carboxylic acids, our sodium borohydride, which we use for our ketones to secondary alcohols, and then the tin HCl for the formation of the phenylammonium ions, followed by neutralization of that acid with a strong base. And that's it. That's the last of the reactions that we need to know.